Section 3.2, percent composition. All right, here we're now looking at not the mass of what a molecule is made up of and getting the total, but I mean we can get the total, that's easy enough, but what percent of that total is copper, or what percent of that total is carbon? Right? Of course, if we add up all the percents, they should equal 100. Right? We're going to account for everything in it. So we're just looking at what percent. Now, the percent is always by mass. It's not by counting of atoms. And for a quick example of that, here's C2H6, which is the formula for ethane, an organic gas, ethane. We can see there's 2 carbon atoms and 6 hydrogen atoms. So if I was to count by atoms, 2 carbon, 6, that's a total of 8 atoms, right? And the percent, well, for carbon, 2 out of 8, that's 25%, or for hydrogen, 6 out of 8, 75%. Right? That would be the percent by counting of atoms, right? When you hear the word percent composition, though, unless they say otherwise, it is always, by definition, by mass, not by counting, by mass. All right, so I got to look at that C2H6, and I got to figure out, well, how much do those 2 carbons weigh? How much do those 6 hydrogens weigh? And then how much does the total thing weigh? And then I can do the percentage from those numbers. So over here, let's go to the mass column here. 2 times the carbon, 12, is 24.022. My 6 hydrogens are 6.048. So my grand total is 30.070 AMUs. So the percent carbon would be that 24 divided by the 30, which is 79.9%. The percent hydrogen would be the 6 divided by the 30, which is 20.1%. All right, so I'm dividing the masses by the total mass and then times 100 to get it to a percent. Right? And notice, sure enough, these do add up to be 100% as they should. All right, so percent composition is by mass. Let's take a look at these examples 3.9 and 3.10 for a little extra here. Going down here, 3.9 and 3.10. Okay. Analysis of a 12.04 gram sample of a liquid composed of hydrogen, carbon, and nitrogen showed it contains that many grams of carbon, that many grams of hydrogen, that many grams of nitrogen. What is the percent composition? All right, well, this is nice. They told me exactly. We don't know what the formula is, but they told me exactly how much carbon and hydrogen and nitrogen are in the whole thing. And so I could add them all up to get a grand total of 12.04. They're not actually showing that, but if you add those 3 numbers up, you get 12.04. So the carbon is the 7. Remember back here they reported 7.34 for carbon. Oh, I'm sorry. When you add it up, they did give you that total right up there, right at the beginning. But you know, if you add these numbers up, you'll get 12.04 too. Anyway, the weight of the carbon divided by the whole thing times 100, 61%. Same thing for hydrogen, same thing for nitrogen. Okay. Let's look at the next example from the textbook here. Aspirin is a compound with this molecular formula. What's the percent composition? Well, okay, 9 carbons, 8 hydrogens, 4 oxygens. I know how to do this, right? So let's see, those 9 carbons, 9 times 12 divided by the whole thing. When they added up the total weight, it turned out to be 180.159. Right? Again, that would be 9 carbons plus 8 hydrogens plus 4 oxygens, 180.159. So they're saying, hey, those 9 carbons divided by the total, which equals apparently 60.00%. The hydrogen, there's 8 of them, so 8 times the hydrogen divided by the total, 4.476%. And the oxygen turns out to be 35.52%. All right, so percent composition, the key there, remember it's by mass, not by atoms, by mass. All right, which leads us to empirical formula. A lot of times when we're doing an analysis, the empirical formula is the first thing that we actually will calculate. And let's just show this by looking at example 3.1 here from my notes. 3.1, or from the textbook, I mean in my notes here. Example 3.1 says, hey, you've got this black mineral. It's an oxide of iron, right? And when they analyzed it, it was 34.97 grams of iron and 15.03 grams of oxygen. Now, assuming that this is a pure ionic compound, or covalent, I suppose, but ionic probably since I've got iron and oxygen, right? What's its percent composition? What's its empirical formula? So what does it actually look like? Like water is H2O, carbon dioxide is CO2. What's the formula for the stuff in this black mineral? All right, well, 34.97, 15.03. Let me go back to my notes here. Where are my notes? There they are. Here's those numbers. What's the empirical formula? Notice that when we write a formula, it would be wrong for me to write, hey, iron has 34.97, so let me just go to some scrap paper here. It'd be wrong to say, hey, I've got iron 34.97, and I've got oxygen. What was the oxygen again? 15.03. So oxygen 15.03. There's the formula. No, that's wrong, because those numbers there are mass, and we don't write the formula of compounds by mass. We write up by counting the atoms. We would say water, H2O, has 2 hydrogen atoms and 1 oxygen. Not that the hydrogens weigh 2 grams and the oxygen weighs 1 gram in it. Okay? And so that would be totally wrong. You can't just throw those masses down. Instead, we have to convert those to counting. And remember, the unit for counting in SI is the mole. Alright, so let's take those masses, 34.97 and 15.03 for iron and oxygen. Let's convert them to moles. Let's convert them to counting the atoms, in other words. I know how to do that off the periodic table. Right? I look at iron. Iron is right there, 55.847. So let's just round it off like the book does. 55.85, and that's fine to do. That's still 4 significant figures. That's plenty. And so 34.97, put a grams on the bottom, moles on the top. That way it cancels correctly. Turns out to be 0.6261 moles of iron. Similar thing for oxygen, 0.9394 moles of oxygen. So now these numbers are indeed counting the atoms. And so in some fashion it is correct now to use those in my formula, and this is what I did in my notes here. Iron 0.6261, oxygen 0.9394. I am counting the atoms, right? But we don't see formulas like that. We like our formulas to be small whole numbers, H2O, CO2, right? We need iron and oxygen in small whole numbers. Now we've got the correct ratio already of atoms of iron to atoms of oxygen. So now it's just a matter of multiplying through or dividing through to get that same ratio, but in whole numbers. And here's the easy trick to always, it will always work if you just do it this way. You look at what you've got, of course you converted them to moles, and now you wrote it out, and you say, okay, let's just divide everything by the smallest of those numbers. So I look at this, 0.6261 is the smallest. All right, so I'm going to divide everything by that smallest number. Of course, 0.6261 divided by 0.6261 is just a 1 on the iron. And if I divide this one, it turns out to be 1.5, or in other words, 1.5, or 3 halves if you want. 3 halves in fraction. Let me actually write that down here. That's 3 halves right there for that 1.5, right? So what do I do next? I say, I need to multiply, because I don't want iron 1, oxygen 3 halves. Nah, I want to multiply to get whole numbers, not fractions. Well, it's pretty easy, I think, to see. I'm going to multiply this by 2. That'll clear away this and give me 3 halves times 2 is just 3. And over here, 1 times 2 is just 2. So I'm multiplying everything through by 2, and that gives me Fe2O3. Now I've got the smallest whole number ratio. There's the empirical formula. Okay. So let's take a look at examples 312 and 313 for a little extra practice here. 312, it says bacterial fermentation of grain to produce ethanol. Okay, so we're taking grain with bacteria, we're producing ethanol, forms a gas with the percent composition. All right, 29% carbon, 72.71% oxygen. What is the formula for this? Here they don't even give me masses, they're just giving me percents. How in the world do I do that? Alright, let me copy this down first and I'll show you. Go back to my notes here. Scrap paper, there we go. You know what? I like to see lines on my scrap paper. That's better. Just, I don't know. I guess it doesn't really matter, right? Alright, let me scroll up here and let's go ahead and do this. We had carbon. That was in this, and what was the other thing in it? Carbon and oxygen. Alright, carbon was 2729. Carbon 27.29%. And the oxygen, they said the oxygen was 72.71. Alright, 72.71%. Where do I go from here? Well, the trick here is, since it's percentages, you could have any total mass you want. I could say, hey, I have a total of 39.62 grams, a billion grams, anything. Percent-wise, it's just the ratio of those. So pick it easy, make it easy on yourself. Let's say I had 100 grams total. If I had 100 grams total, then what is 27.29% carbon, right, of 100 grams? Well, it's just 27.29 grams. So here, that's the trick. If you always assume you always just have 100, then this means I have 27.29 grams of carbon, and over here 72.71 grams of oxygen. And now that I've got the grams, I can convert them to moles and get my empirical formula. So let me actually do this whole problem out for you. 27.29 grams of carbon. We'll go ahead and convert that, grams of carbon, to moles of carbon. Right, 1 mole weighs 12.01 grams. My grams are going to cancel, and that will give me moles of carbon. Let's go over to my calculator here and actually enter that. I've got 27.29, and I'm going to say times 1, divided by 12.01. So divided by 12.01 equals, alright, 2.27 moles. 2.27. Let's do the same thing. That was for carbon. Let's do the same thing for oxygen here. Oxygen, I have 72.71 grams of oxygen. Let's convert that to moles. So grams of oxygen, moles of oxygen. 1 mole weighs 16.00 grams. Where do I get that again? Off the periodic table. Grams of oxygen cancels. Go over to my calculator and let's figure out what that is here. 72.71 divided by 16.00. So that's 4.54 moles of oxygen. So here I've converted it now to counting of atoms. I've converted it to moles. And so my formula is, I guess, carbon 2.27, oxygen 4.54. Yep. Now, the same trick that I've always told you, that I told you before, will always work. To get whole numbers, divide by the smallest number. In this case, I'm going to divide everything by 2.27. That'll give me carbon with just a 1, and it'll give me oxygen. Well, it looks like a 2 to me, but let's just double check that in the calculator. Let's make sure. 4.54 divided by 2.27 equals, yep, sure, 2.000. So 2. There we go. So I've got 1 carbon and 2 oxygens. So it's, well, the empirical formula is CO2. Hey, I know CO2. It's carbon dioxide. Sounds like this gas that was given off was carbon dioxide. Now, keep in mind that's just the empirical formula. Lots of things might have that ratio for the empirical formula. It could also be C2O4, right? Or I could have C3O6. Those are all a 1:2 ratio, right? And so I really, with just the data they showed me, I really don't know that it's not one of those. But since I do recognize CO2 as carbon dioxide gas, it's a pretty good bet that it's probably that one. All right, let's look at the next one, and well, let's see, what did they come up with? Ooh, that must be a picture of this happening. Their solution, they get, hey, CO2 just like we did. All right. Let's look at one last one here. Determine the molecular formula for nicotine. And they gave me these percents again. All right. Now here they didn't say the empirical formula, they told me the molecular formula. Now in the previous problem I got the empirical formula, but that's as good as I could do. Maybe it was one of those other ones we came up with, we weren't sure. There must be something else about this, and so let's read this carefully. Nicotine in plants, addictive nature in cigarettes, 74.02% carbon, that percent hydrogen, that percent nitrogen. And it says if a 40.57 grams of nicotine contains that many moles, what is the molecular formula? So they did give me an extra piece of information. They didn't just give me the percents this time. They gave me the fact that a sample that weighed 40.57 grams had that many moles. All right, so they must have done some additional measurement to determine that. So let me just jump to that first of all before we go any farther here. Go back to my scrap paper here. the sample weighed, was it 40.57? Yeah, 40.57 grams. Alright, so 40.57 grams. And they told me that in that sample there was 0.2500 moles. Now look at this. If I take that and divide it then by 0.2500 moles, look at my units, grams per mole, which is exactly the units of the formula mass. So let's try that. What is 40 divided by 57, or 40.57 divided by 0.25? Go to my calculator. 40.57 divided by 0.25, 162.28. 162.20. Whoops, 28. Got ahead of myself there. 28 grams per mole. I'm going to go ahead and box that because that is actually my formula mass for nicotine. I get that because they gave me the information to figure it out. Now, how is that going to help me? Well, here, I'll show you. Let's go and find keep that in the back of your mind here. Let's go and figure out the empirical formula. We're going to do that the same way like we always do. In fact, I might just steal their solution. They do the same thing, assuming it's 100 grams. So then those percents go to grams, just like I did before. They've converted them to moles. There they are, 6.163 moles of carbon. This is just like the previous example I did. 8.624 moles of hydrogen, 1.233 moles of nitrogen. They found these. Hey, here's the smallest number, so they're dividing everything by that smallest number. They got 571. Okay. And so, actually, they rounded off. It was 4.998, 6.994. Okay, so 571. So at this point, I'm going to go back to my notes. They've got carbon at 5, hydrogen 7, nitrogen 1. All right, go back to my scrap paper. Carbon 5, hydrogen 7, nitrogen at 1. There's the empirical formula. I'll write that up here. Empirical formula is that. What is the formula mass of that empirical formula? Let's find out. I've got 5 carbons, 7 hydrogens, and 1 nitrogen. So I'm going to go to my calculator and type that in. 5 carbons, 5 times 12.01. 7 hydrogens, so 7 times 1.008. And add that to 1 nitrogen. Nitrogen is 14.0067. There's just one of them. There we go. That mass would be 81.12. Alright, so let's see. The formula mass is equal to 81.113 grams per mole. As you can see, whoops, I wrote that. Oh, my pen skipped. There we go. 81.113. As you can see, that mass is not the same as what I know nicotine to be, which is 162. In fact, I can kind of look at that and see it's twice as small, isn't it? The actual nicotine is twice that size. If I didn't know for sure, I would just divide it. Let's try it in the calculator. 162.28 divided by 81.113 equals, 2.000. So this, to go from here to here, I would have to multiply by 2. It's twice as big. So in other words, in the actual molecule for nicotine, there's not 5 carbons, there are 10 carbons. There are not 7 hydrogens, there are 14 of them. And there's not just 1 nitrogen, there's 2 of them. There is the true molecular formula now for that nicotine. So, just review. First, I figured out what is the formula weight for nicotine because they gave me enough information to figure that out. Then we figured out the empirical formula in the usual way, and we saw that, hey, the mass of that empirical formula is exactly half the mass of the true formula mass for that molecule. Therefore, I know that it's a multiple of 2, and so I just multiplied everything by 2, and I got the actual molecular formula for nicotine. So you can get the formula, the empirical formula, from the percents, but if you're going to calculate the molecular formula, not just the empirical, but the molecular, you need that additional piece of information, such as what is the molecular, or I should say the formula mass of the true molecule, and then you can do it. Now sometimes it's times 3 or times 6. All right? It's always going to hopefully be some whole number multiple. If you don't get a whole number multiple, then you've probably done something wrong, in fact. All right.